In this video, we're going to work more example problems related to symmetry and transformations. So let's get started. This first problem says, what word is produced by a 180-degree rotation about the point? So a rotation is one of the three basic types of rigid body transformations that we're studying in this section. You have translations and reflections, which we worked problems on in the previous video. And then there's also rotations, which we're going to work problems on here in this video. Okay, so when a figure is rotated, you always think of it as it's a rotation about a point. So if we think about general 3D space, you can pick any point in 3D space and then think about a figure being rotated about that point. Okay, now, but there's an infinite number of directions you can rotate something about a point. Like in 3D space like this, you could go kind of over the top, to the side, wherever. Now here we're confined to a plane, so if this point was in a plane and we were confined to a plane, well, in that case, there's only, two directions you can rotate about the point, counterclockwise and clockwise. Okay, but so you need to specify the direction of the rotation. But once that direction is specified, then mathematically what's happening when a figure is transformed by rotation is, so let's go ahead and rotate this 180 degrees in the counterclockwise direction. Okay, but not just 180 degrees, but 180 degrees about this point, right? We could rotate it 180 degrees about the center point of the letter O here and do this, right? But no, we're going to rotate it 180 degrees about that point, that blue point. So, okay. It would look something like this as we would be rotating it. All the way till we get to here. Okay, so now mathematically we can understand what has just happened by connecting straight lines from corresponding points to this point of rotation. So, okay, we can see that this bottom right corner of the H here corresponds to this top left corner of the H here. So if we connected those 2 points to the point of rotation here, what we would see is that the angle between these 2 segments is going to be the angle of rotation. So if this was a 90-degree rotation, then we would connect this point to the point of rotation, the corresponding point to the point of rotation, and then the angle between these 2 segments would be 90 degrees. But in this case, it's going to be a straight line because it's 180 degrees. So in this case, if we connect any corresponding points, it's going to be a straight line through this point here. So we can do, those are corresponding points. Those are corresponding points, etc. Right? The center of the O. You see? Every single point on the figure rotated 180 degrees about that center point. That's how you mathematically think about what happens when a figure is rotated. Okay, and so now what word is produced by this rotation? Well, the word how. Okay, what about here? Well, this is going to be, we can see it's going to be the word wow. Okay, and same idea. Corresponding points. The line segments are going to have the same angle between the segments that connect those points to the point of rotation. Okay, what word is produced by a 360-degree rotation about this point? Well, that's going to be, we're going to get the same word back. If we rotate this, it would rotate like this, like it would stay, everything would stay in line with the center point, right? Because let's say we stopped here, then this would be, like a 30-degree rotation. Every single point, if you connected this point of rotation to corresponding points, the angle between the segments is going to be 30 degrees for every single corresponding point. Okay, but we didn't stop there. Kept going. And you just get the same image back. All right, in which direction, clockwise or counterclockwise, will pulley 1 rotate if pulley 2 rotates in the clockwise direction? So, okay, let's do part A. If pulley 2 rotates in the clockwise direction, then pulley 1 is also going to rotate in the clockwise direction because this is, the belt is rotating, is moving to the right here. The belt is rotating like this. It's following this path, which means this is rotating clockwise. But if it's meshed this way, this is interesting. So we can follow this pulley is rotating. So, okay, this would be also clockwise. So if this pulley is rotating clockwise, then we can follow the belt here, and we can see that it's going to mean that the pulley 1 in this case is rotating counterclockwise. Interesting. In which direction, clockwise or counterclockwise, will gear 1 rotate if gear 2 rotates in the clockwise direction? So, okay, gear 2 is rotating in the clockwise direction, and so gear 2 is pushing gear 1 to rotate in the counterclockwise direction. So it's different from a belt connection. A meshed gear connection is a little different from a belt connection in that sense. Okay, now here we've got pulley 2 is pushing pulley 3 to make pulley 3 rotate in the, since this is rotating clockwise, pulley 3 is going to rotate counterclockwise, but that's, pulley 3 is pushing pulley 1 to rotate in the clockwise direction. Describe the types of symmetry displayed by each of these automobile logos. Okay, so in a plane, we've got line and point symmetry. So this is really interesting. So, okay, let's see. So, all right, so the Toyota symbol looks like we're going to have a line symmetry for sure. Yeah. You can connect, every point has a corresponding point in terms of the perpendicular bisector relative to this line here. So there's a line of symmetry down the center, but we're not going to have a horizontal line of symmetry, right? We can take this point here, perpendicular bisector, we don't have a corresponding point, so it looks like that's the only line of symmetry. Okay, now point symmetry, let's see. So the center would be the point of symmetry would have to be somewhere in here. So, okay. Does that have a corresponding point? I guess so. Maybe so. Maybe so. Well, no. Okay, if we took this point here and we tried to find its corresponding point, yeah, that's not going to work. I think this here is not symmetric is the issue, right? Because again, I could take this point and it's not going to have a corresponding point relative to a point of symmetry, because the point of symmetry is going to have to be somewhere around here. So no point of symmetry, just a vertical line of symmetry right down the center here. Okay. Now the Chevy logo, it's tempting to say, okay, yeah, it's going to have a vertical, maybe even a horizontal line of symmetry, but no, because you've got, if we take this point, for example, and we want to find its corresponding point relative to the vertical line of symmetry, well, we're going to come to about right here, the perpendicular bisector. So no. And same idea with the horizontal line of symmetry. If we try to find the corresponding point here, it's not going to work. So, okay, we'll come back to lines of symmetry, but let's think about a point of symmetry. So it's going to have to be right somewhere in the center, And it looks like it's going to have point symmetry. Yes, yes, it will. Because we can find a corresponding point relative to this point of symmetry anywhere, right? So yeah, you can tell this looks symmetric into some sense, this Chevy logo, and so yeah, it's point symmetry. But there's no line symmetry, I would say. I don't think. I mean, maybe something like that. Well, no, okay, yeah, this isn't going to work because take this point, perpendicular bisector. You're going to be off the, like, okay, yeah, this point right at the edge here, right at the edge. See, it's not going to work. So only a point symmetry. All right, now what about Volkswagen? Looks like it has a line symmetry right down the center. And does it have a point symmetry? It looks like that's the only line symmetry. What about, does it have point symmetry? So, okay, it would be right in the middle there. And, okay, looks like yes. Yes. Interesting. Right, we can find a corresponding point relative to this center point here for any point on the logo. So yes. So we've got one vertical line of symmetry right through the center, and that's it on the Toyota for the Toyota logo. Here we've got no lines of symmetry, but a point of symmetry at the center here. And then here we've got a vertical line of symmetry and a point of symmetry. And that's it. Again, just note that there can be multiple lines of symmetry for the same figure. You can have no lines of symmetry, one line of symmetry, or more than one. You can have 5 lines of symmetry for a figure, however many there are. Okay, but when it comes to points of symmetry for any figure, there's going to be either no points of symmetry or one point of symmetry. Okay, same problem here. Let's identify all the types of symmetry associated with these logos. Let's start with the easier one in the middle here. So this is definitely point symmetry for sure. It looks like there's like infinite number of line symmetries. Is that right? So would there be symmetry about... Yeah. I mean, so this has an infinite number of lines of symmetry and also has a point of symmetry as well. Cool. Okay, let's see here. We've got... This looks like it's going to have no symmetry. Definitely not point symmetry because, you can just see right here. Well, that might barely make it. But then if we do, what about this? No way. Okay, what about line symmetry? So, well, okay, yeah, it'll be symmetric with respect to a horizontal line. Yeah. But other than that, no. I mean, you might think something like this, but no. Because you could take a point right on the edge here, and that's not going to work. So just this horizontal line of symmetry. Now here we've got a vertical line of symmetry, a horizontal line of symmetry. I think there would be a point of symmetry at the center here. Let's see. So yeah. Yeah, a point of symmetry, and then let's see. Are there any other lines of symmetry? So would this, like a diagonal here, something like this, would that be a line of symmetry? So no. I mean, we could, okay, what corresponds to this point right here? Doesn't have a corresponding point. So that should be it. These two lines of symmetry and a point of symmetry. So we've got a horizontal line of symmetry here, and that's it. Here we've got, this is like infinite symmetry, a point of symmetry and like an infinite number of lines of symmetry. Any line that you draw through the center point is going to be a line of symmetry. And here you've got a vertical, horizontal line of symmetry going through the center, and then a point of symmetry. Given a figure, which of the following pairs of transformations leads to an image that repeats the original figure? So earlier in the video, we saw an example of this and with a 360-degree rotation. About any point, a 360-degree rotation would result in you get the same image back. Okay, but let's take a look at each of these and see if we can deduce if we'll also reproduce the exact same image. All right, so the figure slides 10 centimeters to the right twice. No. So that's like, so if we, okay, so like if we rotated this 360 degrees, we get the original image back, right? Now, but if we slide this 10 centimeters to the right, and now we do that same slide again, we get this. Now, this is a rigid body transformation, so these two figures are congruent, but they're talking about the original figure. So like they lie on top of one another, so no. Okay, let's see. Let's now reflect this about a vertical line twice. Yes, you are going to get the original figure back. So if let's mirror this. Okay, so that's reflecting about like the center line of this computer screen here. Okay, so now if we mirror it again about that same vertical line, we're going to get the image on the other side, which is going to be the original image. There you go. I just mirrored it about a vertical line twice, and you get the original image back. If you mirror something about any line, not just a vertical line, any line twice, then you're going to get the original image back. Okay, figure is rotated clockwise about a point 180 degrees twice. Yes, you're going to get the original image back. And you could do this about any point. So that's a 360-degree rotation is what they're saying, right? Okay, it rotated 180 degrees once. And in this case, you actually get the original image back, but that's because this box is symmetrical. Like we could, okay, let me draw something. Okay, so if we rotate this 180 degrees, we don't get the same figure back. In general, unless there's some form of symmetry involved, like with the previous figure, in general, we're not going to get the same figure back. But if we rotate it 180 degrees, well, that was counterclockwise. Let's do clockwise. Same thing, though. So there's 180 degrees clockwise. Don't get the same figure. Now rotate it 180 degrees clockwise again. There you go. You get the same figure back. So this is, we've got, so okay, no, yes, yes. Now, okay, rotating it 90 degrees clockwise about any point, we could rotate it about any point, and we get the same result. So we could have chosen to rotate about this point. It doesn't matter. In this case, no, because we're going to be rotating it a total of 180 degrees. And in general, you're not going to get the same figure back, as we can see here. So, no. Okay, same question, but some different scenarios. So let's go ahead and bring back this figure here. So, okay, part A, the figure slides 10 centimeters to the right, followed by a slide of 10 centimeters to the left. Yes. 10 centimeters to the right, and then go back 10 centimeters to the left. You're back on the original figure. Figure is reflected about the same horizontal line twice. Yes, you could. If you think about it, you can reflect about any line anywhere in 3D space. any line oriented in any way in 3D space, if you reflect about that line once and then reflect that figure about that line again, you're going to get the same figure back. So, yes. Okay, figure is rotated clockwise about any point 120 degrees twice. So what's 120 times 2? That's 240. So no, I mean, unless you rotate 360 degrees for a general figure, you're not going to be getting the same image back. So, okay, rotating it clockwise, 360 or some integer multiple of 360. So, all right, let's do 240. What are we doing clockwise? So 180, there's 180, and then now 240, we need to go another 60. So let's go down to 120. You know, no. So no here, but then the 360 degrees twice, yes. Yeah, I mean, any integer multiple of 360, that's what this is. This would be what? 720? You're going to get the same image back, rotating about any point in the same direction. No, you couldn't, if you rotated a certain amount in one direction and a certain amount in another direction, then it's going to depend on what the net rotation is, right? A regular hexagon is rotated about a centrally located point, as shown. How many rotations are needed to repeat the given hexagon vertex for vertex if the angle of rotation is these 4 different rotations? So how many rotations are needed to repeat the given hexagon vertex for vertex? Okay, so what they mean by that is we can, because of the symmetry of this hexagon, we could rotate it and, you know, look, it repeated. But that's not what they're saying. They're saying, like, okay, if we mark off this vertex, we don't have a repeated hexagon until we do this. That's what they're saying. So if you've got 30-degree rotations, then how many rotations do you need to apply consecutively to repeat the hexagon? Well, okay, it's 360. To repeat the hexagon, vertex for vertex, you're going to need to, is that what they're saying? Let me check. Hold on. Yeah, that's right. So how many times do we need to rotate the hexagon consecutively 30 degrees until we've got this exact same figure here in terms of this vertex is at this same location as where it started? Well, okay, for part A, it's just 360 divided by 30. So 12. So if you apply this rotation 12 times, you'll have the exact same figure back. Okay. Okay, here 360 is divisible by 60 as well. So we can just do 6 times 6 is 36. So this is going to be 6 rotations. Now 90, this is going to be 4 rotations to get a 360. Now this is a little bit different because we're going to have to go past 360. How many rotations 240 degree rotations do we apply until we get to some integer multiple of 360 is the idea, right? Because you'll repeat this figure vertex for vertex if you rotate it 360 degrees, 720 degrees, any integer multiple of 360. So what we'd see here is that this would be, so 240 times 2 is 480. 240 times 3 is 720. There you go. So that's 360 times 2. So if you rotate this 3 times, apply this rotation 3 times, you'll be back at the original position, vertex for vertex. Okay, same problem here. And, you know, I guess they're trying to confuse you by changing the shape, but if the shape doesn't matter in this case at all. They could have asked us this, if you think about it, they could ask us this question for any figure, it doesn't matter what it is. I mean, if we're just thinking about like in a plane, it still wouldn't matter in 3D, but you have to kind of specify in the question that, you know, constraining the rotation to the same direction. But think about it. If we had any figure here, it wouldn't matter what it is. Wouldn't matter what it is. If we're not saying that, okay, look, like if it would matter between the hexagon and the octagon if we were counting that, look, when you get congruent figures back in terms of orientation as well, right? So we could rotate this if they were saying that, look, we're counting this as an equivalent figure. Okay, well, in that case, then we'd have two different problems between the hexagon and the octagon. But if we're talking about vertex for vertex, it's always going to be a 360-degree rotation to get a truly equivalent figure as far as even the orientation of the corresponding points being in the same spot. It's going to, you have to rotate 360 degrees. So it doesn't matter that we have an octagon here. It's the same problem. It's, okay, how many times do you need to apply a 10-degree rotation to get to either 360 degrees or some integer multiple of 360? So 360 divided by 10 is 36. 36 rotations. Okay, what about 360 divided by 45? That's going to be 8. Yeah. Okay, 90 is going to be 4. And 120 should be 3. 120 times 3. There you go. They're just trying to trick us here by changing the figure. Angle A prime, B prime, C prime is the image of angle ABC following the reflection of angle ABC across line L. Okay, if the measure of angle A prime, B prime, C prime is given by this expression here of x, and the measure of angle ABC is given by this expression of x, find x. This is interesting. Okay, so let's see. We can take a... Let's try and make this general. So I'm going to put some slanted line here. There's line line L. Okay. Now we've got an angle here, which we know an angle is in general just represented by two rays with a common endpoint. Okay, this is angle ABC. We want to put the B in the middle there. Okay, we'll call that angle theta. Now, if we reflect this, then is it going to change the angle? Well, yeah, this is actually a really good question. If we reflect in any angle, will it change the actual angle measure? And the answer to that question should come from the fact that we've been talking about how all of these transformations we've been doing in this section have all been rigid body transformations, right? All of the figures are congruent. The resulting figures are congruent, whether or not you do a translation, a reflection, or a rotation. Well, that's the essence of congruence. It doesn't change angles, side lengths, right? So we can absolutely reflect this, and the angle's not going to change. It's going to be, we can go ahead and do it. Okay, perpendicular bisector to the line. Just try and estimate. It looks about right. Okay, perpendicular bisector. Okay. Those actually happen to line up. I didn't mean to do that. But that's fine. Just get it halfway. Somewhere like that. So, okay, there's a point. There's a point. Okay, and let's see. This is point. This is the vertex. Okay, so the corresponding points are B prime, and then this was A prime would be over here, and C prime over here. But again, it's a rigid body transformation. The angles are going to be equal. The figures are, if you do a rigid body transformation, a translation, a reflection, a rotation, the figures are congruent. meaning the angles between the features don't change. The side lengths don't change. So to find x, we just need to set these two angles equal to each other. So x divided by 5 plus 20 is equal to x divided by 2 plus 5. So let's multiply this entire equation by 10. So we've got 2x plus 200 is equal to 5x plus 50. So subtracting 2x from both sides, we've got 3x plus 50 is equal to 200. So 3x is equal to 150. X is equal to 50. Angle x prime y z prime is the image of angle x y z following a 100 degree counterclockwise rotation of angle x y z about point y. If the measure of angle x y z is given by this and the measure of angle x prime y z prime is given by this, find x. So yeah, we've got, this is the same exact problem that we're just going to set these two equal because this was just a rigid body rotation, but we can go ahead and draw this out. So you've got angle x prime y z prime. Okay, so here's this angle theta. Now, if we rotate it about point y 100 degrees counterclockwise, there's 100 degrees. Okay, like that. So now here we've got, this is, well, okay, no, we started with x, y, z. X, y, z, and this transformed into x prime, but y is still y, z prime. Okay, well, the angle doesn't change, right? It's a rigid body transformation. So all we need to do is just set 5x divided by 6 equal to 130. 130 times 6, 780. So 5x is equal to 780. So 156 degrees. Yeah, I guess that'd be in degrees. There you go. Hexagon ABC, B prime, A prime, D. ABC, B prime, A prime, D, okay, is determined when the open figure with vertices A, B, C, and D is reflected across segment DC. Okay, I see. So what they're saying is that, so you reflect this across that line DC, and you get this new figure here. So you started with A, B, D, C, and you still, D and C are still the same vertices, but now you have a new, you've got B prime and A prime. So this hexagon A, B, C, B prime, A prime, D is created when you reflected the open figure, because it was open because this was open, right? It started open, and you get this new figure here. You reflected the open figure A, B, C, D about the line, that dotted line DC. Okay, so now how many diagonals does this have? Well, okay, we can use the formula for the number of diagonals of a polygon from the polygon section, because remember that formula applies to any kind of polygon. This is a concave polygon, that's fine. Or no, is it concave? No, actually this is convex anyway, but this would apply to convex or concave. So the formula was the number of diagonals is equal to n times n minus 3 divided by 2, where n is the number of sides of the polygon. So we have 1, 2, 3, this is 6. This is a hexagon. So 6 times 6 minus 3 divided by 2, 6 times 3 divided by 2, 18 divided by 2 is 9. So 9. Oh, wait, no, this is concave. I'm going crazy. Yeah, that's a reflex angle. These are reflex angles. But still, you can use that diagonals formula applies for any polygon. So it's 9. Now, how many of the diagonals, these 9 diagonals, lie in the exterior of the hexagon? Well, there are going to be some that do because this is concave. So there's 1, there's 2, and that should be it. 1 per reflex angle. 3, 4, 5, 6, 7, 8, 9. Yeah, 2. Rectangle BCAC prime, BCAC prime, is formed when the right triangle ABC is rotated as shown. Okay, so take ABC and rotate it in that direction, and you get BCAC prime, right? Because now you get this. So the angle of rotation in that case was 180 degrees. And the center point of rotation was, you could see right in the, at the center of the circle. At the center of this circle, or like at the center of the hypotenuse. You can see where that center is?